Airspeed measurement. If a symmetrically shaped object were placed in a moving airstream, the flow pattern typical of figure 1.4 would result. The airstream at the very nose of the object would stagnate, and the relative flow velocity at this point would be zero. The airflow ahead of the object possesses some certain dynamic pressure and ambient static pressure. At the very nose of the object, the local velocity will drop to zero, and the airstream dynamic pressure will be converted into an increase in static pressure at the stagnation point. In other words, there will exist a static pressure at the stagnation point which is equal to the airstream total pressure, ambient static pressure plus dynamic pressure. Around the surface of the object, the airflow will divide, and the local velocity will increase from zero at the stagnation point to some maximum on the sides of the object. If friction and viscosity effects are neglected, the surface airflow continues to the aft stagnation point where the local velocity is again zero. The important point of this example of aerodynamic flow is existence of the stagnation point. The change in airflow static pressure which takes place at the stagnation point is equal to the free stream dynamic pressure, lowercase q. The measurement of free stream dynamic pressure is fundamental to the indication of airspeed. In fact, airspeed indicators are simply pressure gauges which measure dynamic pressure related to various airspeeds. Typical airspeed measuring systems are illustrated in figure 1.5. The pitot head has no internal flow velocity, and the pressure in the pitot tube is equal to the total pressure of the airstream. The purpose of the static ports is to sense the true static pressure of the free airstream. The total pressure and static pressure lines are attached to a differential pressure gauge, and the net pressure indicated is the dynamic pressure, lowercase q. The pressure gauge is then calibrated to indicate flight speed in the standard sea level air mass. For example, a dynamic pressure of 305 pounds per square foot would be realized at a sea level flight speed of 300 knots. Actually, there can be many conditions of flight where the airspeed indicator does not truly reflect the actual velocity through the air mass. The corrections that must be applied are many, and listed in sequence below. 1. The indicated airspeed, IAS, is the actual instrument indication for some given flight condition. Factors such as an altitude other than standard sea level, errors of the instrument and errors due to the installation, compressibility, etc. may create great variance between this instrument indication and the actual flight speed. 2. The calibrated airspeed, CAS, is the result of correcting IAS for errors of the instrument and errors due to position or location of the installation. The instrument error must be small by design of the equipment and is usually negligible in equipment which is properly maintained and cared for. The position error of the installation must be small in the range of airspeeds involving critical performance conditions. Position errors are most usually confined to the static source, in that the actual static pressure sensed at the static port may be different from the free airstream static pressure. When the aircraft is operated through a large range of angles of attack, the static pressure distribution varies quite greatly, and it becomes quite difficult to minimize the static source error. In most instances, a compensating group of static sources may be combined to reduce the position error. In order to appreciate the magnitude of this problem, at flight speed near 100 knots, a 0.05 psi position error is an airspeed error of 10 knots. A typical variation of airspeed system position error is illustrated in figure 1.6. 3. The equivalent airspeed, EAS, is the result of correcting the calibrated airspeed for compressibility effects. At high flight speeds, the stagnation pressure recovered in the pitot tube is not representative of the airstream dynamic pressure, due to a magnification by compressibility. Compressibility of the airflow produces a stagnation pressure in the pitot which is greater than if the flow were incompressible. As a result, the airspeed indication is given an erroneous magnification. The standard airspeed indicator is calibrated to read correct when at standard sea level conditions, and thus has a compressibility correction appropriate for these conditions. However, when the aircraft is operating above standard sea level altitude, the inherent compensation is inadequate and additional correction must be applied. The subtractive corrections that must be applied to calibrated airspeed depend on pressure, altitude, and calibrated airspeed, and are shown on figure 1.6 for the subsonic flight range. The equivalent airspeed, EAS, is the flight speed in the standard sea level air mass which would produce the same free stream dynamic pressure as the actual flight condition. 4. The true airspeed, TAS, results when the equivalent airspeed is corrected for density altitude. Since the airspeed indicator is calibrated for the dynamic pressures corresponding to airspeeds at standard sea level conditions, variations in air density must be accounted for. To relate equivalent airspeed and true airspeed requires consideration that the equivalent airspeed coupled with standard sea level density produces the same dynamic pressure as the true airspeed coupled with the actual air density of the flight condition. From this reasoning, it can be shown that TAS squared times lowercase rho equals EAS squared times lowercase rho naught. Or TAS equals EAS times the square root of lowercase rho naught over lowercase rho. Or TAS equals EAS times 1 over the square root of lowercase sigma. Where TAS equals true airspeed, EAS equals equivalent airspeed, lowercase rho equals actual air density, lowercase rho naught equals standard sea level air density, and lowercase sigma equals altitude density ratio. Or lowercase rho over lowercase rho naught. The result shows that the TAS is a function of EAS and density altitude. Figure 1.6 shows a chart of density altitude as a function of pressure altitude and temperature. Each particular density altitude fixes the proportion between TAS and EAS. The use of a navigation computer requires setting appropriate values of pressure, altitude, and temperature on the scales, which then fixes the proportion between the scales of TAS and EAS, or TAS and CAS, when compressibility corrections are applicable. Thus, the airspeed indicator system measures dynamic pressure and will relate true flight velocity when instrument, position, compressibility, and density corrections are applied. These corrections are quite necessary for accurate determination of true airspeed and accurate navigation. Bernoulli's principle and the concepts of static, dynamic, and total pressure are the basis of aerodynamic fundamentals. The pressure distribution caused by the variation of local static and dynamic pressures on a surface is the source of the major aerodynamic forces and moment.